Hello all, welcome to our channel. So in this video, we will talk another interesting topic for hardware engineers. So when we use regulators, right, we always talk about compensation resistors and generally what most of the designers do is they just go by the recommendations of the data sheet, calculate the capacitor, and then they'll just use it. But it is important that they need to understand why this compensation is done. So if you have a little background of border plots, the control system theory, then it is very easy to understand. So before that, let us just look at this. Where do we use compensation in regulators? So generally when we do this, right, the compensation is used in the output feedback loop. You generally see like some capacitor used in parallel with the upper resistor of the feedback, or some regulators might have a special pin for compensation. So this is very commonly used, and we use some capacitors in the PF range, NF range to compensate. So again, the capacitor value depends on how much compensation we require. Now, why do we need that compensation? That's the major question, right? Yes, compensation is required, and then we place a capacitor across the resistor. But why do we need that? That's the very important point that we need to know. For that, we have to understand the kind of systems that are there in our general usage. So generally, for any system, or in fact for some of the systems, we have a feedback, right? The feedback is like could be a positive feedback or a negative feedback. So if you take the example of an oscillator, we have positive feedback, and then like for an op amp, we have something called negative feedback, right? Even we use the negative feedback, and then we do have the gain under control by using a negative feedback. So if you have a positive feedback, that means you're increasing the gain. That means you are producing something extra at the output. Whereas in the negative feedback, we are like controlling the gain and doing something such that the system is stable. So these two kinds of feedbacks are there. So now, while we talk about those systems, the regulators that we use in our applications have a negative feedback. So while we're talking about positive feedback and negative feedback, what is the figure about this? That we need to understand, right? So here, if you see, there are two lines. So this is one, the red line that you see here is called the gain margin, and gain plot, and then the dotted line is called the phase plot. So they are plotted against frequency. If you see here, the x-axis is the frequency, and then the gain axis is on the left, which the waveform refers to, and then on the right you have the phase. So phase is always in degrees. So now, if you see here, when we studied about control systems, or we might have read about this border plot, and we might have talked about the frequency, right? So we talk about the center frequency, right? Where this is the frequency at which the gain is at 0. That means, as we show the mouse cursor here, this is the point. You can see here that is 0. So this is the point where the phase margin should be very good, such that you have a stable system. So that's the actual criteria. So now if we'll just go to the next slide. While we talk about that center frequency, you can see here the actual gain plot crosses zero. Gain is zero means that means beyond that it is all negative feedback. So when gain is zero, you can see here the difference to the phase margin. So gain zero is at around example minus 60, and then till the phase it is zero. That means there is a phase difference of almost 50 degrees. So this is how we calculate the phase margin. So based on different phase margin values, the stability of the system depends. So important parameter mainly is the phase margin. So if you see this, what phase margin is better for a regulator? So ultimately, when you design a regulator, right, you must have a stable output. You should not have any overshoot, undershoot at the output, and you should not have any oscillations. Like generally, when we have some noise on it, we call it the ripple in regulator terminology. But when you take a overall control system, we talk about the overshoot, undershoot. Which basically is the ringing, and then there could be some variations at the output, unnecessary variations. So and ultimately the output should be stable, there should not be any variations. That's the bottom line, right? So if you see here, there are different phase margin values: 20, 30, 45, 60, 72. So for a phase margin of 20, if you have a phase margin of 20, that means you have very high ringing on the output. So you have that overshoot, undershoot, and then ringing happens. And then if you have a phase margin of 30, ringing is somewhat under control, but you still have the ringing at the output. If you have a phase margin of 45, that means there is no ringing, no oscillations at the output. Your response time of the particular system is good, and it is a critical damping condition. That means ultimately the oscillations have subsided, and your output is good. So 45 is what we mean. And then when we go to 60, you see that you have a very good phase margin. And if you plot your gain margin and phase margin, gain and phase plots, if you get 60, that means you are good to go. And then if you have 72, you have ultimate output. That means very, very stable output, and you need not bother about the system. So that's how, based on the phase margin, we do decide on the stability of the system. So understanding these critical damping, over damping, under damping, and these bode plot parameters, you need to go to the control system theory and just learn a bit. The damped oscillations, all these are terms which we read in our academics. So it's just application of those. The main point is that this is the phase margin which is better. Now the point is, let us assume here we are saying the phase margin for 60 is good, and here we approximately said around 50-55 phase margin is there, which is also acceptable. Now if I want to vary the phase margin, what we are going to do? So in the next video we will talk how to improve that phase margin and what the design engineers do and compensate the regulators. So hope we gave an idea of what is a phase margin, and then how it is important and why compensation is required in regulators. Please post your questions. Please post your comments on the video. If you have any other information that you know about this, please post in the comments. Please like and subscribe to our channel. Thank you.